Okay, I think it should. Okay. Yep. So screen should be shared. Should I get started?
Yes, please go ahead and get started. Thanks, you, Joshua.
Okay. Yep. So I'm going to talk about Fermi-GBM in the era of multi-messenger transients. And I want to start by just briefly introducing what Fermi-GBM is, which is an instrument on board the Fermi Gamma Ray Space Telescope, which actually consists of two instruments shown on the left of this slide here. There's the Large Area Telescope on top, and then below that there's the Gamma Ray Burst Monitor, or GBM, which is the instrument that we'll be talking about today, which consists of 12 sodium iodide detectors sensitive to gamma ray photons from 8 keV to 1 MeV, and 2 BGO detectors sensitive to gamma ray photons from 200 keV to 40 MeV. And the strength of this type of instrument is that it monitors the entire unocculted sky, so that's everything that isn't blocked by the Earth in that picture on the bottom right there, looking for short, on the order of seconds to minutes, gamma ray transients. And then once you account for the full orbit of the spacecraft, it covers the entire sky every 90 minutes and provides localizations for these transients to within a few degrees, which is okay. It's not great, but the strength here is the ability just to capture huge swaths of the sky looking for these short transients. And kind of, the strength of that is shown on this next slide here, which is the overview of the GBM science that we do, where what I'm showing are the number of our scientific triggers as a function of time, where each color represents a different physical phenomena that we're observing with this instrument, from gamma ray burst all the way up to galactic sources, with the most relevant class of events for this talk being the short gamma ray bursts. And the reason for that is we're kind of going to look at things from the multi-messenger perspective here, and it turns out that short gamma ray bursts are these really nice multi-messenger sources. And so to kind of delve into that in more detail here, here's kind of the multi-messenger perspective of GRBs from kind of the simplistic artist rendering, where what the GRB looks like is on the left, you have the central engine, which is a black hole, providing the energy input to a relativistic jet as it accretes material and kind of throws blobs of it out, because black holes are messy eaters, onto the direction of the spin axis, which forms this relativistic jet. Eventually, at a certain radius, those blobs start colliding, which create internal shock fronts that can accelerate charged particles, that then give off gamma ray photons as synchrotron radiation. When you hit a certain radius, the particle densities are low enough that those gamma ray photons can escape, and we can measure them with Fermi-GBM, which is what's highlighted by that green box there. And then at later times, as this jet expands out even further, you eventually get X-rays and visible light and radio waves from the interactions that happen with the surrounding material. And so, at a base level, these sources are really good multi-wavelength sources. And where the multi-messenger perspective comes in is that for short GRBs in particular, we now know that at least one set of objects that leads to short GRBs are these binary neutron star mergers, where you have two neutron stars in spiral, releasing gravitational waves, and they eventually collide and form the black hole that then launches your GRB a couple seconds later. And so that's kind of confirmed. And then in principle, though, in addition to the gravitational waves, there should also be neutrinos being produced in these jets as well, just on the basis of you have this very powerful jet. There are charged particles in it, some of which should be protons. And if the conditions are right, you should be producing neutrinos that in principle should be observable here on Earth. We have not detected any neutrinos from a GRB yet, but the sensitivities of neutrino instruments are improving all the time. So hopefully one day we can have kind of the trifecta here of gamma rays, gravitational waves, and neutrinos all from the same object. That would be wonderful. And that would be for a kind of triple detection of a short GRB. The last thing I'll mention here is that there is another progenitor class to these GRBs, in particular the long GRBs come from core collapse supernova. Those won't necessarily produce gravitational waves, but they could still produce neutrinos if you get the right conditions and if you have the sensitivity to detect them. So those are currently multi-wavelength sources. They could eventually become multi-messenger sources as well. But that said, kind of the key multi-messenger science here that we're going to focus on are going to be these joint detections of gravitational waves and a GRB from a binary neutron star merger, which is what's shown in this video playing here. We have the in-spiral of the two neutron stars until they collide, forming a black hole, launch your jet for the gamma ray burst. That kind of blob in the middle that you saw come out, that's actually an optical kilonova event that can happen as well. And then finally with the optical afterglow and X-ray afterglow once you hit the external medium there at the end. And so, that's kind of the picture that we have here. And we know this from this one detected event, GW170817, which is a gravitational wave event that had a gamma ray burst counterpart, 170817A, following 2 seconds after it. And so that's what's shown in the plots on the top right on this slide, where the two top event rate plots with the blue curves, that's the rate of gamma ray events with the gamma ray transients highlighted in red there, coming 2 seconds after that merger time at t equals 0 from the gravitational wave time frequency map. And so we know these events are from the same object because they come roughly, the gamma ray burst comes the expected amount of time after the merger of roughly 2 seconds for some of the models. And then on top of that too, if you look at the localizations of the gamma ray burst and the gravitational wave event, they're coming from the same spot on the sky. And on top of that, we observed the optical kilonova transient, which is also expected to be produced by this event. And so, everything lines up. This is this nice, clear detection of a gamma ray burst associated with a gravitational wave event with, tons of additional measurements being made here in optical, X-ray, and radio as well. And so you can ask the question, what did we learn from this one event? Turns out quite a bit. So we learned that binary neutron star mergers are progenitors to short gamma ray bursts. We got some constraints on the size of the gamma ray emitting region and the gamma ray burst based on the timing of this event, constraints on the speed of gravity, Lorentz invariance, Shapiro delay. And then we also have an explanation for the origin of heavy elements from the subsequent optical kilonova event that happened too, where you essentially have an explosion that throws out a bunch of neutron-rich material. Those neutrons collide and can create heavy elements. But from this one event, there's still plenty of questions that remain to be answered, such as the rate of these types of short GRB kilonova events via the binary neutron star merger. This one event in particular was actually notably dim for a gamma ray burst at the distance that it was observed. And so we know it was viewed off axis, but we can't quite constrain what the edge of that jet that we're looking down looks like, whether it's some sharp fall off, smooth fall off, or something that's a bit more isotropic. And then kind of the last thing here that we'd still like to learn more about is the time delay between that gravitational wave and the gamma ray burst to understand the modeling for the launch of this jet and how you produce the gamma ray burst. And so kind of the straightforward way of understanding these additional questions is, we need more joint detections of these events. We only have one so far. And to that end, fairly recently, the gravitational wave detectors completed their third gravitational wave observing run from April 2019 to March of 2020. There was an 8-fold increase in the number of gravitational wave events that are likely to be astrophysical, the most important of which are going to be the identified binary neutron star events, of which there is one, and then to a lesser extent, the neutron star black hole events, which can also produce electromagnetic emission under the right conditions, that as long as your neutron star doesn't get immediately swallowed by the black hole. And so what we did in Fermi-GBM is we followed up this new set of events looking for additional joint GRB gravitational wave detections. And so the kind of at the most basic level, the search is straightforward. At the start, we just look for, are there any onboard GRB triggers that we just normally trigger on in real time? Were there any events near any of these gravitational wave events? And there were none within 10 minutes. So there's no kind of convincing onboard triggers that could be a GRB associated with these gravitational wave events. So then we dig further down into our data using a fancier likelihood technique that we call the targeted search. It's our most sensitive method for extracting GRB-like candidates from our data set using an external trigger time from the gravitational wave event. The plot in the bottom left shows what that looks like, where kind of that dark blue is the likelihood ratio number, which is quantifying the likelihood that you have a GRB transient, where darker is more likely. And in this case, for this example, this is the one known event 170817, where you're highlighting in that nice dark region where the actual transient happened. What it looked like for 03 is actually what's on the bottom right of this plot, where that likelihood ratio, the observed likelihood ratio from the full 03 sample is essentially consistent with the 68% confidence region around background. So nothing interesting there seen in 03. We do not have any convincing counterparts to any of these gravitational wave events during that third observing run from the gravitational wave detectors. So, without any convincing detections, we can at least set upper limits. And so here is what that looks like for this one binary neutron star event from 03, GW190425, where what this plot is, this is the flux upper limit placed by Fermi-GBM at every point on the sky, where that blue region is the part that we can't see because it's blocked by the Earth. So the purple are our flux upper limits as a function of sky position. And then the green contours, that's the 90% credible region of where the gravitational wave detectors believe this binary neutron star event could have happened on the sky. And so we cover a good chunk of that, roughly 60% of it, but not all of it. And so, it's possible that we missed this one event. And so to kind of, help us out with that in case we did miss it, we actually joined forces with this complementary instrument called SWIFT-BAT, where BAT stands for the Burst Alert Telescope. It's a more focused instrument, so it views a smaller portion of the sky, but has a higher sensitivity to lower fluxes than GBM and has much better localizations. And so kind of combining our information with theirs, we can produce a joint upper limit map from both instruments, where SWIFT provides this additional coverage for its portion of the sky that's covered by its field of view, highlighted in this black circle there. So it gives us a little bit more additional coverage, a bit higher sensitivity. But here we were a little bit unlucky in that it didn't really cover that missing part of the gravitational wave contour on kind of the left side of that blue region there, which, that happens. It just depends on the configuration of the satellites at the time when your gravitational wave event goes off. And so, in other scenarios, looking on here, sometimes you win some where that additional coverage from SWIFT gives you the full view of this gravitational wave localization. And in other cases, you get really unlucky, and it seems like nature is working against you. And you get cases like the bottom right there, where the gravitational wave detectors believe this event to have happened, 191103, actually almost exactly circles where SWIFT was looking. So it's purposely trying to avoid being discovered by that SWIFT-BAT instrument. But that's kind of why we're doing our best in coordinating with as many instruments as possible to make sure we don't miss these events as best we can. But we're kind of given the hand we're dealt sometimes. But that said, there is some additional information here that we can include. So assuming that the binary neutron star event happened at least within our visible portion of the sky, you can combine our flux upper limits with the distance to the estimated distance to this event and compare the equivalent isotropic luminosity for this binary neutron star event 190425 with that of the one measured event 170817A to see if it's constraining. In this case, it's not, because the upper limit is above that measurement. And then, so that's unfortunate. And then we have these other reasons for the non-detection, which are the partial sky coverage. And then also this is jetted emission, so we don't necessarily expect to observe every binary neutron star event, because some fraction will miss us just from the jet pointing not directly at the Earth. Okay, so that said, that's kind of the perspective for binary neutron star events. And then the last thing that I wanted to mention here is that even though we're kind of unlucky with observing these small numbers of binary neutron star events, within this 03 run, there's a huge volume of binary black hole events that were also observed, which are not necessarily expected to be good candidates for producing gamma ray bursts, because it's really hard to create the jet in the environment where these binary black hole mergers typically occur. But there were a few claims to potential counterparts, and so we wanted to investigate, given the sheer number of non-observations that we have during 03 of these binary black hole systems, can we put constraints on just some of these more exotic scenarios for gamma ray burst emission from binary black hole events? And so that's what's shown on the right of this slide here, where each panel is a different type of scenario, which could in principle give you a gamma ray burst following a binary black hole event, with the top one being kind of the most physically motivated, though I should caveat all of these as they're quite exotic. So the top one is this charged black hole model, where you can form a gamma ray burst using a charged black hole. That second one down, that's a neutrino anti-neutrino annihilation-driven wind jet. That one is kind of a bit more exotic. It doesn't make any claims over how you get the GRB. It just says this is a typical jet emission scenario. Assume you get the right conditions to form it. What would the corresponding gamma ray burst flux be? And in that case, it turns out for this one event, 1912-16, given how close it is and how massive it is, it's really hard to avoid not seeing it. And so in that case, we can put a constraint on that one model. And then for the other models here, there's a Blanford Zanayak model, I think. And then just a model where we scale the gamma ray burst flux with the total energy of the gravitational wave system. And so, yeah, in this case, we can start ruling out kind of this one exotic scenario for this neutrino anti-neutrino annihilation-driven jet. Yeah, where kind of these populations for the panels on the right, those are coming from, we essentially simulate the full population of possibilities for forming a gamma ray burst from the various measured parameters that we get from the posterior distributions of these binary black hole systems, plus assumptions about some jet opening angles there. Okay, cool. So that said, that brings me onto my summary here. And so, hopefully I've convinced you that these gravitational wave instruments, Fermi-GBM and SWIFT-BAT, are working together to enhance the number of joint GRB gravitational wave detections here, which are these really nice multi-messenger sources. We don't have any significant detections of a GRB counterpart to a gravitational wave event from the third gravitational wave observing run. Our BNS and SBH limits, upper limits, are not really constraining, but we are being able to rule out some of the more exotic emission models for binary black hole mergers. And we're rapidly coming up here on the next observing run of the gravitational wave detectors 04, which will provide additional opportunities for a joint detection of the BNS event. The statistics are still expected to be low. It's essentially one event plus or minus one. But we got to try. There's a lot of rich science to learn from these objects. And so every one that you can get is really important. All right, thank you.
Wonderful. Thank you very much, Joshua. If we do we have any questions from the audience? You can either raise your hand on Zoom, or if you want to type a question in the chat, we can ask it that way as well. And maybe to kick things off, first, thank you for this wonderful talk. I have a question. This is getting a little detailed, but about the beaming, in the sense that obviously presents a real challenge if these things are strongly beamed to be able to, and it actually maybe gives us a sense of how fortunate we were to detect 17. I can't remember the 170817. Although, as you mentioned, it's seen off axis. Do the gravitational wave solutions give you any indication of what the inclination of the resulting accretion disk might be, and therefore what you would expect the beaming angle to be? And can we use that to put some additional constraint on there?
Yep, so they do. So when you make these gravitational wave measurements, you model a bunch of different configurations, which include different inclination angles. And so the gravitational wave measurements will report a distribution of possible inclination angles. If you have a really bright detection, that distribution can be more constrained. But for this one event from 03, 190425, it's a pretty distant event, so it's actually pretty weak. And so it's not very well constrained. It's essentially the 90% credible region contains angles out to 70 degrees off axis. Yeah. And so it is hard being able to constrain that from the gravitational wave measurements if it's kind of a more distant object. But that said, there are competing ideas over what does this off-axis emission look like. One of the ideas that we're pretty sure that we can at least rule out is there's a group that argues for more isotropic emission from this cocoon-based model that they call. And so, if that were true, we expect to see lots of these things. If it's not true, we don't expect to see as many. And so once you can build up a population of them and say how many do we actually observe, you can actually start ruling out these off-axis emission models, even if you don't get additional detections.
Great. Thank you very much. Do we have any additional questions for Joshua? I've got one follow-up to that over here, which is 04 is going to be more sensitive, right?
Mm-hmm.
So it'll have a larger horizon, but also presumably can do a better localization of the sources. And so this particular issue, or maybe more generally, just getting the constraints on the binary merger parameters, how much will that, in addition to the larger number of objects, how much will the improved sensitivity to the merger parameters help in terms of building in these gamma ray constraints that you've got here?
Right. So what O4 does is it makes observations like the one that we already had, that one from 2017. That event will appear brighter in the gravitational wave measurement because it's a more sensitive instrument. So you get a better localization for that type of event. But that said, most of your events will always be near threshold, the way kind of it works out. And so yeah, the kind of the anticipated localization for most things, it's actually the same regardless of you're talking about 02, 03, 04. It's going to be around 1,000 degrees on the sky for your typical event.
Great. And so we have one last question for Joshua from Cheris Hall, who asked, do we think that in the future will LISA detection of gravitational wave events, might that provide better candidates for detecting GRBs? And I'm thinking maybe, detecting things prior to the merger at lower frequency could help with that. Do you have any thoughts on that?
Yeah, so LISA, right, yeah, you're going to have information even before the merger. So you'll know where your GRB is going to go off. And so that will help with pointed instruments. You can actually tell them where and when to look. But yeah, I think we'll still have a bit of this problem where, I mean, LISA's, you're just getting more and more sensitive with your gravitational wave instruments. And we need to work on the sensitivity of our gamma ray instruments in the sky. And that is something that many groups, both in the US and Europe, are working towards. Because we know it's an issue going forwards, especially since the two kind of premier instruments that we have been using, Fermi-GBM and Swift-BAT, they're now teenagers, so they're 14 and 18 years old. And so yeah, we do need replacements, and we need more sensitive replacements.
Great. So thank you very much, Joshua, for a wonderful talk, and everyone thank Joshua again on Zoom if you can. Let me share my screen again. Share this one. So our next talk, there we go, is by Lindsay Demarchi from Northwestern, who's going to tell us about the Tale of Supernova 2004C. And before Lindsay begins, just to ask everybody again, for those who arrived a little bit late, if you're interested in giving a frontier talk in the coming months, our next one will be in February, please have a look at this Google form or you can look at this QR code, and please sign up to give a talk. Once you're on the list, you'll be considered for future talks basically in perpetuity. And we would love to have lots of exciting science get presented in future seminars. So I will stop sharing. Lindsay, if you can share your screen. Wonderful. Take it away.
Awesome, thank you. Let me just actually get this like centered and not messy. Sorry about that. This is what I get for doing something fancy with Zoom. Okay. Awesome. Thank you everybody for having me and for coming to listen on this afternoon. It's raining here in Chicago. But yeah, as Ryan was saying, I'm going to talk about the Tale of 2004C, which was originally the title of my talk, and then I lost literally everything on my computer. So this has been remade in another visage, but it's the same talk. But as we said, I'm Lindsay Demarchi. I'm a graduate student at Northwestern University. And there I work with both Raffaella Margutti, who's now at UC Berkeley, and Shane Larson. With Shane, I primarily do actually gravitational wave and multi-messenger work with LISA objects, but this talk is actually a multi-wavelength talk about a particular supernova that exploded in 2004. So if you're a radio person like me, there's going to be a lot of radio in this talk, but I also included a little bit of some optical stuff if that's more your wheelhouse and what we can look forward to when LSST comes online. Okay. So to understand where I'm actually coming from with this conversation, you first need to understand what's been broken in the field and in the literature. So imagine you have a star, and that star has a pretty thick envelope or atmosphere, and it's full of atoms. And if we zoom in on one of these atoms, we would see all of its electron orbitals. Okay. Pretty basic. If an electron absorbs a photon, then that electron is going to move up in energy level. But in a star, you have loads of electrons and you have loads of photons. And what actually ends up happening is a sort of net pressure away from the surface of the star. So with all of these different atoms in the atmosphere of the star and all of these interactions happening, this net pressure away results in something called mass loss. All stars undergo mass loss, and this particular mechanism is nicknamed line-driven winds, kind of historically, because as you can imagine, it's going to depend on how many electron orbitals you have that can act as a sail for these atoms. So it's going to depend on metallicity. And it's also going to depend on how many photons you have to kind of play around with, or the luminosity of the star. So this particular mechanism of mass loss, called line-driven winds, kind of historically, because metallicity is metals, is spectroscopic lines, it's kind of a stretch, but line-driven winds depends on metallicity and luminosity of the star. So if I plug in solar metallicity and really high luminosity, like 10 to the 6 solar luminosities, I get an upper limit of how much mass my star can lose per year due to this mechanism. And that number is 10 to the -4 solar masses per year. Yet we see all the time, nature does not really follow such a gentle release of mass to its environment. So this is a real Hubble image of a Wolf-Rayet star. And even if I don't put numbers on it, you can tell that that's a lot of material kind of suddenly around the outside of the star. We've seen specific examples of this paradigm-breaking behavior many times. Like, I am not the first person to say this. So one example is a cousin of 2004C, 2014C. That is as confusing as possible, but 2014C encountered an entire solar mass of material in its CSM about 10 to the 16 centimeters away from the star. The supernova I'm talking about is 2004C, and it encountered 2/100ths of a solar mass in its CSM. And if you're like me, you hear that and you're like, that is extremely underwhelming. I'm sorry that I'm not talking about a whole solar mass. That was kind of my expectation when I was doing this research, but it was brought to my attention that 2/100ths of a solar mass is still a ton of material. If a star lost 2/100ths of a solar mass every year, that star couldn't live to be more than a couple thousand years old. So it's still a lot of material to be losing. And it's just, kind of another data point in this vast array of supernovae that seem to encounter large shells of material in its CSM. So the plot that you're looking at is from a recently published paper that, I guess the first thing to point out is that all of the points with error bars on them actually come from radio data from the VLA. And without really needing any imagination at all, if you look along the x-axis, all the way to your left would be the location of the star, and all the way to your right would be infinity. And so on the y-axis is a story of that density that is encountered in the CSM at this distance from the star. So you see a consistent density that then starts to taper off. If the material was deposited in the CSM by line-driven winds, or by winds at all, it would fall along one of these diagonal lines on the plot. So the first thing you might notice is there is a strange horizontal departure in the density profile of the CSM that does not align with any of these diagonal lines, but maybe kind of towards the outer edge, it sort of does. So I've highlighted in gold that mass loss rate just to kind of guide your eye. So that would be 10 to the minus 2.5 solar masses per year. The large red elephant in the room is the fact that line-driven winds are all the way at the bottom of the plot, meaning that this is not a sustainable mechanism to create this kind of CSM, apart from the fact that the density profile itself doesn't match. However, I have very tantalizingly placed these like green points really close to the line-driven winds. That's kind of it's kind of not fair. So these green points here should have the same error bars as the other data, but they don't, because I didn't want them to look too much like believable points. And the reason is that when you're modeling data from radio observations, you have to make a decision about your energy budget pretty much. So you're measuring this energy that's coming from radio wavelengths, and you have to decide how you want to partition that energy. And historically, what people have done is they've said, let's just put a third of that energy into electrons, a third into the magnetic field, and a third into protons. And that's called equipartition, 33% to each. But nowadays, we don't, based on like models and people who are more in the theory side of things, have decided that that's actually not very accurate. And you should put 1% to the magnetic field, 10% to electrons, and the rest of the percent to protons. It's very, very different. So when you don't use equipartition, you get the darker points. When you do use equipartition, you could convince yourself that something near line-driven winds is happening, apart from the fact that the density profile doesn't work. But like I said, I'm not the first person to bring this up or to have observed this. So this is a plot that I stole from Daniel Breithauer 2022, but also along the bottom are a whole bunch of citations that have just been from the last 5 years of people who have discussed strange amounts of material in the CSM of these supernovae. And what Daniel Breithauer did with his plot was took from all over the field evidence of this happening and mapped out at what location from the star this is happening and how much mass was deposited in that CSM. And what you actually come to find is that all types of supernovae do this. It ranges from type 1bc, type 2b, superluminous supernovae. All stripped envelope supernovae seem to encounter material in their CSM. So the picture that I want to leave you with is a star explodes. And when that star explodes, the fastest blast wave of all the material, the fastest material forms a blast wave that moves about 10% the speed of light. And it catches up to material in its CSM somewhere on the order of 40 days after it has exploded. And when it does that, it encounters the material that has actually been lost somewhere between hours to thousands of years before the star exploded. So if this blast wave is traveling really, really fast, if this material was lost somewhere between 10 to 1,000 kilometers per second, that means that you're looking back at somewhere between hours to thousands of years before the star exploded. So in a way, this radio shockwave is a probe of the final moments of a star's life. And so I come back to this plot now to bring your attention to the very top axis, where I assumed a velocity for that material that went into the CSM. And I said, okay, I've got a distance and I've got a velocity. So what I could do is roll back the clock and figure out how long before the supernova exploded was this 2/100ths of a solar mass deposited in the CSM. The result that I found was that this shell is 3,000 days old. That's like 2 to 3 years old. So it's truly the final breaths of a star right before it died. And if you wanted to assume a different velocity of how that material got there, again, it would be somewhere around 1,000 years, which is still very much the final moments of a star before its explosion. And this is the power of radio astronomy, and especially late time follow-up of certain transients. So if you're like me, or if you're like Daniel Brethauer, or if you're like Ralph Margutti, you want to know, okay, 1,000 to maybe even a couple years before the star exploded, what was the star doing in its core? What was going on that could have produced some kind of instability that would lose this material? So this is for 2014C, this plot here. And what they did was that these vertical lines are the location or look back time of the shell. And these are for a whole bunch of different models from Shiord and Quartet 2014. And what they found was that you could actually get an estimate of what kind of core burning was happening at that period in time. So this is, again, just to remark on the power of radio follow-up and radio astronomy of supernovae. I promised some LSST, or at least an LSST slide. So I wanted to also bring up the example of 2016 GKG, and this is a plot that I stole from Charlie Kilpatrick, 2021. So I've highlighted with this little like green circle here, a set of data points. So everybody else has been, this is photometry, everybody else has been offset by a certain magnitude, but the one that I've circled in green, you can read as is. That's an apparent brightness of 15. You don't have to like move it around in your mind. And what you see is that the light curve itself started to decay in time like a supernova does, and then it hits this black bar where we don't observe it anymore. And that black bar is 21 mag, which is about the limit of what SDSS can do. That's where a lot of this follow-up, or ground-based astronomy, I guess. The stars come from Hubble, so they don't count. So 2016 GKG was located pretty close. It was about 26 megaparsecs away. So we got really lucky that we could observe this to the point where we suspected that it was interacting with its CSM and we could trigger radio follow-up. Excellent. But if 2016 GKG was located instead 100 megaparsecs away, the light curve that we would have observed would look like this. And you see that the good stuff, or even around 40 days where we would want to start triggering, is getting really close to 21 mag. However, 25 mag, so sorry, this is about where 40 days is. This is about where interaction started to occur, just to kind of guide your eye. 25 mag is the limit of LSST. So if 2016 GKG was located 100 megaparsecs away, we still would have been able to capture the entire evolution of the supernova, and we would have been able to trigger follow-up. So this sort of exercise is to say that as LSST comes online, I expect that we'll be able to observe many supernovae out to late times, many more supernovae that are far and for longer, which then would mean that we get to trigger more radio follow-up and start to fill in the parameter space of what mysterious activity is going on so close to the star. So just to wrap up, I want to leave you with a lingering question, which is, why do such diverse progenitors of different supernovae seem to share a death rattle? And that is a question that I hope will be answered very soon in the coming years. Thank you very much.
All right, thank you very much. And thank you, Lindsay, for all the effort in recreating your talk. We appreciate that, and this is really interesting. We have a question from Roseanne. Please go, you can unmute.
Oh, hi, Lindsay. That was a great talk. Thanks for that wonderful overview. So you did cover all of the stripped core supernovae, including the ones that are of type 1B, 1C. Now, what I'm thinking about is 1A models where you may not have specifically had stripping, but in many of the single degenerate models, we think that there are epochs that last for a long time where mass may be ejected from the system. And, there may be periods where it's high and low. So you may have shells, or you may have something like a continuous ball of gas and dust with varying density as you go out. So I just wanted to ask you about the prospect of exploring this with radio, or in your opinion, has this question already been adequately explored?
Oh my God, that's a great question. Yeah, so I think what's tricky both about the 1A question and like even in the case of 2004C is this question of like, how much could be responsible, like if you go the binary route of a binary progenitor, that kind of opens up some options. And can we have the same options if we go, you know, the single degenerate route? And I think this is actually the power of multi-wavelength astronomy, because unfortunately, radio astronomy, when you take those measurements, your mass loss is degenerate with your wind speed, which means that the amount of material is degenerate with how quickly that material was put there during the star's life. So I have in my appendix here a plot that I made. This is with software that I wrote to look at radio data that I think would be very interesting to also apply to the situation where you're talking about, because this is kind of the opposite of the other plot I was showing. This is where I took the mass loss rate, held that constant, and let the wind speed change.
Mm-hmm.
And here it tells a story of, I don't know if you guys can see my cursor, but it tells a story of early times in the star's life having one velocity, and at late times in the star having a faster velocity that caught up to the slower wind. And so what you actually get in that situation is like a sculpting. You're creating a traffic jam in the CSM of faster wind that caught up to slower wind. And the whole reason I bring this up is to say, if it was actually just a change in wind speed, that kind of changes the implication of the amount of material you would have to lose. So where you were bringing up like, you know, these episodic like cycles of losing tons of material. Mm-hmm. If you just simply have a knob and you actually turn wind velocity instead, you don't need to lose so much material to create a shell. I don't have to eject something wholesale. I just need to change the speed of how that got there and the way that it kind of comes. So to me, that could mean something about the way that the star is evolving itself, because from what I understand, it's very hard to eject a lot of material. Mm-hmm. I don't know if you've seen the same thing in studying 1A progenitors.
Mm-hmm. Well, in 1As, the difference really is probably, well, two things. You know, both in single and double, you probably have a common envelope. And so then there's a question of how long takes place. What is the duration of time between the common envelope ejection and the supernova of whichever type it is? And in both cases, there is a period where there's a lot of mass loss. In the double degenerate case, it would be prior to the common envelope, maybe through some winds in a symbiotic. And in the single degenerate, it could occur right up until before the supernova. So you have this continuous thing. And I love your relating, you know, the possibility of different speeds to different types of shells. So what I would suggest, and maybe we can talk about this later, is to really think about the options here.
Das Ganze auf YouTube dann angucken. Das heißt, das sollten wir auf jeden
I'm not sure what's happening there.
Got some background.
Yeah.
Okay.
Okay. So no, I was finished. I just wanted to say, I think that this work is extremely interesting, and it would really be nice to see the implications for the 1A progenitor problem.
Yeah, absolutely. Yeah, I would love to talk, especially because 1A progenitors are what I also look at from a multi-messenger perspective with my LISA work. So I think there's a lot to talk about, actually.
Wonderful. Thank you.
Thank you very much, Roseanne.
Wonderful. Do we have any more questions for Lindsay? John Raymond.
Hi. There are also supernovae that have dense CSM much closer to the star, where you see the sort of a bump in the light curve after just a few days.
Yeah.
Do those correspond to, say, a different phase, like it would be oxygen burning or something like that? I didn't really have time to see what was going on in that plot that showed for instance, the helium burning and so on.
Yeah, I can pull that plot back up. What I would say is, do I have to go through the whole thing? Here we go. That's kind of the struggle with this particular supernovae. And I would say actually a lot of supernovae in general, for whatever reason, seem to have this density of material specifically around 10 to the 16 centimeters. And a lot of that close in material is like 10 to the 14, 10 to the 15, like it's a couple orders of magnitude closer to the star. So that's one of the puzzling kind of pieces of evidence, like why, to me, that is like much closer to the time of explosion and a different core burning phase. The other thing about that is that you kind of open up the opportunities for many different sort of mechanisms. So one of my favorite mechanisms is by Jim Fuller, this idea of gravity waves, not gravitational waves, but different instabilities because of core burning can trigger these pulsations that travel through the star and launch material. And those seem to get angsty, I guess, towards the end of the star's life when you have more core burning kind of flipping on and off more quickly to the star's death, or much more close in time to the star's death. And that would deposit material that's within this like 10 to the 14, 10 to the 15 range. So I would say in general, the answer to your question is yes. But in this particular supernovae and with many more, we're finding it's not, the time scale doesn't really line up.
Okay, thanks.
All right, thank you for your question.
Wonderful. We have any last question here? I have one quick question for you, Lindsay, which is the from the point of view of your research, you mentioned that LSST can go a lot deeper, so both go farther in time to watch these interactions or to see objects that are farther away. And what you personally, what would you most like to do with these data? Do you have a particular kind of supernova, or a particular type of analysis that you're most excited about once we start getting this fire hose of data from Ruben?
Yeah, that's awesome. Yeah. I think it could be very interesting to take entire populations of certain types of supernovae. So like 2004C was a type 2b, meaning that it was partially stripped at the time it died. But I just recently did this on a whole population of 2N supernovae, which have narrow lines because they're interacting with something real close by. And I did not find very much evidence for circumstellar interaction, which is odd. So I think that as time goes on, we might be able to fill in more specific characteristics about supernovae types at late times. But I think that the real plug that I want to make is for observational astronomers to not lose interest when something's done exploding, because I think part of the problem is everybody moves on to the next thing and we forget to do late time follow-up because it's not as flashy and cool, I think. So that's more of a social thing I would like to see is more people excited about late time follow-up.
Wonderful. So thank you very much. Let's thank Lindsay and Joshua again, both for wonderful talks. I'll just share screen one more time here. Just to say once again, a final plug for anyone who's interested, please sign up to give a talk. We had excellent attendance today, 50 or 60 people, and that's typically been what our attendance is. So thank you for those for joining us. Please encourage your friends and colleagues to come join our seminars and also to sign up to give a talk. And we'll be back in touch with information on the timing of the talks in February and in months going forward. So thanks everyone again, and have a wonderful weekend.